Welcome everyone. So I am Alex Friedland. I am here in Santa Barbara as one of the organizers of the Neutrino program. I work up in the Bay Area at SLAC, which is a laboratory that's run by Stanford and Department of Energy. And so I'm gonna give you an overview, a historical overview, if you'd like, of this fascinating subject of catching neutrinos from exploding supernovae, and the future prospects. And other people here will tell you many other interesting things about what that neutrinos can tell us. This will be, I'll try to be mostly non-technical by the standards of this program, but I'm open to answer any more detailed technical questions offline or during the discussion. So this story begins about 166,000 years ago, when the Earth was in the grips of the Ice Age, and in a small galaxy, not too far away from our galaxy, a large star suddenly undergone a huge explosion. But of course, on Earth, we didn't know that until much later, because the light takes a long time to propagate. And it was propagating for all this time, and finally arrived here 35 years later. And so in February of 1997, a few astronomers were looking at this small galaxy, which is called the Large Magellanic Cloud, and they were getting ready to take routine pictures of this galaxy. But there was a problem. They saw something very bright in front of this galaxy. So they thought that maybe there's something wrong with the telescope. So a guy who was on duty stepped outside, looked in the direction of that galaxy, and to his amazement saw a bright star right in front. And so, the long story short, this was a discovery of a supernova explosion, which was the first supernova explosion since Kepler that was visible by a naked eye. So the person on duty at that time was named Ian Shelton, and he got very excited, and after that he decided to enter graduate school. So this, event has prompted hundreds and thousands of physics papers, and it was a major development in astrophysics. But at that time, it was just a stunning phenomenon that people could see. Then they realized it was a supernova, informed other telescopes, and then telescopes all over the globe started seeing this explosion. Now, this is a neutrino talk. So the question is, what was observed with neutrino telescopes? Now, it turns out, in addition to telescopes that were looking for light, there was also another kind of a detector. There are actually two of them that were running at the same time, and they were very different from what you expect from a telescope. They were tanks, large tanks of pure water that were buried deep underground. This one in Japan, and it was called Kamiokande. And another similar detector was called IMB for Irvine, Michigan, and Brookhaven collaboration. And this one was in the US. So there were large tanks of very pure water that were buried deep inside the respective mines. There's a dark volume of water surrounded by photomultiplier tubes. And these photomultiplier tubes were waiting for faintest flashes of light. So why were there such detectors built? So it turns out that in the 70s, there was a burst of theoretical activity in particle physics, where a suggestion was made that the strong force, which holds nuclei together, which binds particles in the nucleus, and the other two known forces, the weak and electromagnetic, were part of one big unified picture. So this is one of the famous papers of that time, which said that never mind what SU5 is the gauge group of the world means, just that there is some description of all these forces. And this description made a startling prediction that protons are not perfectly stable and should decay. So the prediction of that, if you got a huge volume of matter and put it somewhere deep underground where it's shielded from the outside, mostly cosmic rays, then every now and then you would see these tiny flashes would come from proton decays. And so this was an experimental race to observe this. So, well, the IMB detector came online in 1982, so that was 40 years ago. And the Kamiokande detector came online a year later. And they were ready to detect a proton decay with an astonishing half-life of about 10 to the 31 years, which is much longer than the age of the universe. That's why you need this large volume to have any decays. And to the greatest disappointments of both of these collaborations, this prediction at that time did not pan out. So they did not see the proton decay. And then the question in front of the experimentalists, well, what else could these detectors do? So you made an amazing investment. You built a detector that's unlike anything else. You were ready to go to Stockholm to collect your Nobel Prize, and you don't see it. So then the idea was that why don't we look at something that at that time was known as the solar neutrino problem. So let's, what is the solar neutrino problem? So there is something, a problem or a discrepancy that by that time had already existed. So there were first measurements of this in the late 60s, 1967. And that effort was really led by a small group of amazing scientists. And the experiment that they were doing was something like this. So you take a tank of fluid. In their case, it was filled with 100,000 gallons of fluid that's basically dry cleaning fluid. It was a fluid that had a lot of chlorine in it, where chlorine was the nucleus that they wanted. And they also put it in a remote mine, which at that time was an operating gold mine in the Black Hills of South Dakota, about a mile deep underground. And their goal was to measure neutrinos that were produced in the sun. And that this problem was known as the problem of missing neutrinos. So the hypothesis was that processes generating energy in the core of the sun release, in addition to the energy, also release elementary particles called neutrinos. These neutrinos had amazing properties that they could get through the sun and to the Earth, and very few of them were expected to interact in the detector. So they would cause a small number of chlorine nuclei in the giant underground tank to convert to argon. And then the task of this experiment was to extract every argon atom that was created in this manner, count them, and by doing this, detect neutrinos created by reactions in the sun. So the theorist on this collaboration, his name was John Mccall, he had made a prediction. And the prediction was that in this Olympic-size pool of cleaning fluid, you would have 51 argon atoms made every month. Not very many. And then the experiment of Ray Davis, who was the lead experimentalist on this collaboration, was extracting these argon atoms and counting them, and he found only 17 or so per month. And this discrepancy was first reported in the late 60s, and then it persisted year after year since that time, and became known as the solar neutrino problem. So you can say, well, what does this mean? So since this is a teachers' conference, there's a scientific method flowchart that we in science are supposed to follow. I learned this when I took my kids to the Children's Museum. So the the flow chart goes like this. You make an observation, you have a hypothesis, experiment, and conclusions. And then if you reproduce the experimental result, then you learn something new about the world, and you modify your theory. And if you don't agree, then you say maybe the experiment was flawed, or maybe the hypothesis isn't correct, and then you go to this cycle. So the problem is that the physicists in charge were extremely stubborn. So Ray Davis performed many calibration measurements of his detector and said that I think that I am capable of extracting argon atoms and counting all of them, which is a great feat. And the theorist, John Mccall, was similarly checking his solar model and trying to account for various uncertainties. And he said, I also don't see a problem. So at this point, you say, well, you know, there is something going wrong here. So maybe what we should do is we should reproduce this experiment by other ways, or we should have a different model of the sun than what these people have. But, you know, science is done by real people. So there was no experiment to follow up this in the immediate aftermath. And there were people who were trying to modify the solar model, but none of these modifications were correct. So this came to be known as the solar neutrino problem, that the measurement was low. And so the follow-up experiment was needed. And remember, now we're going back to the 1980s. So there are these giant detectors. And so they're already on the ground. And they use different technology from the Homestake experiment that I described by Ray Davis. But in order to make this detector suitable for looking at the solar neutrino problem, they needed to make a number of significant upgrades. So they needed a better water purification system, new electronics, and an additional layer of photomultipliers outside, which were called the veto layer in the technical jargon. So anyway, a bunch of upgrades had to happen. And these upgrades were finished by January 1987. So serendipity has a huge role in this part, because if you remember, a few weeks later is when the supernova explosion happened. So then once this was observed, the neutrino experimentalists knew what they had to do. They went back to their data and they looked in the time window around the explosion. And indeed, they observed 11 interactions in this Kamiokande detector in a 10-second window. But interestingly, this 10-second window preceded by 2 hours the first optical observation of the explosion. And then there were 8 more interactions in the IMB detector and 5 more in another underground detector called Baksan scintillator telescope. So that's what, for Kamiokande, this is what their data looks like. There is a rate of background, and then there is a spike of events. As I said, this happened 2 hours before the first optical observation. And as a function of energy, you could measure the energies of these different neutrinos. The energy in this field is measured in mega electron volts, which are suitable units. So you can see there are measurements at the 3 detectors as a function of time. So as I say, about a 10-second time window, 12 seconds to be exact. Now you may worry that the events at Kamiokande are lower energy than IMB. You'd be right to ask what happens here. As I said, that Kamiokande spent time to improve their detector. So their energy threshold was lower. They were sensitive to lower energies. So they were able to catch these guys, but they were a smaller volume. Whereas the IMB detector was a larger volume, but their sensitivity threshold was higher. So actually these 2 stories are consistent with the properties of both detectors. And so if you look at these 24 events and you do some processing of this information, you confirm that in this distant star, there was a phenomenon that technically is a gravity-powered neutrino bomb. So let's talk about what we mean by that. So, okay, the gravity-powered neutrino bomb went inside a massive star. So what is the role of gravity? And what are neutrinos that we've been already talking about? And why are they important in this explosion? So at the basic level, you need to know how a star works, a normal star, before we talk about supernova explosions. And the main thing is that, well, star is a blob of gas that's held together by universal gravity. It's the same force that's pushing us down, is pushing this blob together. And if there is no balance, no resistance to this force that pushes it together, you can estimate how quickly such an object would collapse about 1,000 seconds or so. Now you can ask, you know, your students, advanced students, or maybe not so advanced, to make this estimate. And here's an example of how such an estimate could go. You would say that when things collapse, the kinetic energy of things and the potential energy of gravitation are about the same for a typical moment when things collapse. And then from this, the time of the collapse is the typical radius of the object divided by this typical velocity. And you put this together and you recover several laws that you may know. So there is a ratio, there is a time here of collapse, which it depends on the radius to the power of 3/2. So this is one manifestation of Kepler's laws, that the periods of the orbit's squares are related to the cubes of the semi-major axis. That's this way it's known as a Kepler's law. And in terms of the average density of the object, it's in this way, it's the law of Hubble expansion of the universe. So a simple estimate of that type can give you insights into many things. When I show this to undergraduate students, or these types of estimates are done all the time in physics, and they form the basis of, you know, how a physicist approaches the problem. But when you show this to an undergrad, they think there's some cheating involved because you're not writing the exact equation, you're just using twiddle arguments. And the more you learn about physics, the more you realize that these are, you know, this comes from profound understanding of what's going on. And in many cases, this skill is crucial in becoming a physicist. So that's why I'm doing this example here. Anyways, there is a time scale that's related to gravitational orbit period or collapse. They are the same at this level. There's a factor of a small order one factor that distinguishes them. So the same principle that tells you that the period of a satellite in the near Earth orbit is about 10 to the 3 seconds. The same principle that tells you the sun would collapse on this time scale. So by the way, there is a so I asked my kids who are educated in the US about the first space flight. They said, oh yeah, that Armstrong guy. I said, no, not the walk on the moon, the first space flight. Silence. So I said, well, what about Yuri Gagarin? My daughter said, oh yeah, I saw that name as one of the Russian books that are around our house. Anyway, this is the 61st anniversary of the first space flight, and you can look up on Wikipedia. It takes about 100 minutes, took about 100 minutes, including takeoff and landing. So that period is related to the average density of the Earth or the sun. Okay, anyhow, so we know the sun does not collapse on this time scale, and in fact, the age of the solar system is estimated to be 4.7 billion years. So something is counteracting gravity in the case of the sun, and that something is internal pressure. Things have to be exactly balanced. So the sources of internal pressure are, you know, the most obvious source is you just have a gas inside, which is hot. And the hotter the gas, the more pressure it exerts. And so you can compute how hot the interior of the sun must be in order to balance this gravitation. Here is another simple argument. You make the kinetic energy of the molecules, compare them to the average potential energy of protons inside the sun, and you get 10 to the 7 Kelvin, and the actual number is 14 million Kelvin in the core of the sun. So this is the sun. The sun is held in perfect hydrostatic equilibrium, as we say it, by the fact that its interior must be hot. But if the sun is you can think of this as a balloon that balances tension with internal pressure. In terms of heat, it's not a perfectly hermetic balloon because stars leak heat. So the heat is stored in the stellar interior and it diffuses out. It's very good for us. So this, you know, the fact that we have life on Earth owes directly is owed to the fact that the sun, the interior, loses heat in this diffusion. But then without the sources of heat to replenish, the star would have to contract and contract and contract. This was actually a situation in physics in the 19th century. So there were great physicists like Kelvin Helmholtz. They estimated the lifetime of the sun that you would find if you said that the gravitational potential energy is what powers the sun, what gives you the heat, and you take this gravitational potential energy that you estimate from solar mass and radius, divided by the observed solar luminosity, you find about 30 million years. So this gave Charles Darwin, among many people, a lot of trouble because he had a theory of evolution, but it needed longer time scales than 10 million years. Anyway, that was before we knew other sources of energy in the sun. And in the 20th century, there was a major development that we discovered that nuclear processes could give you additional sources of energy. And now we know that stars are fed by thermonuclear reactions in their core. So basically, there was a discovery in 1920 by Francis Aston that 4 hydrogen nuclei weighed slightly more than a helium nucleus that is assembled of 4 nucleons. And then using Einstein's E = mc² formula, it meant that there was if 4 protons are brought together and become 2 protons and 2 neutrons, this excess mass could be converted into energy. And so there were a number of physicists like Arthur Eddington, Hans Bethe, George Gamow, that developed the theory of stellar generation based on this. So there is a thermonuclear reactor in the core of the sun. It is there just to replenish the heat lost through the surface. So in stars, one of the big problems that we have been unable to solve on Earth with thermonuclear energy, namely containing the plasma and making this process self-regulating. In stars, this problem is solved. So this process is perfectly self-regulating. So the rate with which the sun burns fuel is related not by the nuclear reaction rate, but by the rate with which the heat is lost. Basically, you keep burning hydrogen into helium at the rate necessary to correct for the heat lost. So, okay. And then for massive stars, the story is the same, but they're more massive, so they require more pressure. So the heat must be higher. And the model tells you that they evolve much faster. So you keep burning hydrogen, and once hydrogen is exhausted, this core contracts until helium can burn into carbon and so on. So a massive star at advanced stages of its evolution looks something like this. It's an onion. These layers are not to scale. This iron core in the center is much smaller than the outside. But basically, it looks like an onion, right? So you have hydrogen burning in the shell to helium. Then inside, the temperature is hotter, and you have carbon, neon, oxygen, silicon, and eventually iron. So So at the late stages of evolution, a massive star looks something like this. And by the time you get to iron, it's a figure you get from a wiki, the number of nucleons in a nucleus. And you can see that iron is the most efficient element. So by going to this side, you don't gain any more energy. So after you make this iron core, nuclear fusion stops being effective. So then there is an iron core, and it grows. And there is an amazing fact about our universe, that when this core reaches a certain magic number, about 1.4 times the mass of the sun, this core can no longer sustain itself, and gravity wins it, and it undergoes collapse. So this is known as the Chandrasekhar mass limit. It's a beautiful fact about our universe, that this limit exists. For those interested, it has to do with relativistic degeneracy pressure of electrons. And then when this object becomes sufficiently massive, electrons become relativistic and they're not able to sustain the gravitational pressure. So then this core loses pressure support and collapses. And then what happens next? So the question is, can we ever be sure? So there is a core of the sun, which of this massive star, which undergoes this amazing collapse. And so how do we know? Because this core is shielded from us in visible light by outer layers. And so even in the case of the sun, the nuclear reactor is not directly visible. So we had to, people said that we should build neutrino detectors to look at that. So I explained it like this to my kids. If you have a guy like that, and you'd like to know how big his heart is, well, if you can do an X-ray, that's great. But looking on the outside, it's not easy. So if you're looking at an exploding star from the outside, it's kind of a yak. So you need a way to X-ray the stars, and so that's what neutrinos do for you. So Mccall and Davis were trying to look in the core, in the center of the nearest star, our sun, and using neutrinos as a thermometer for the solar core. So this is a beautiful idea, originally by Bruno Pontecorvo in 1940s. And the key process, as I said, is you take protons inside the sun and you burn them. First, you make deuterium, which is a bound state of protons and neutrons. And then in order to balance charge, you can create a positron. And then it turns out that when you make a positron by weak interactions, it comes paired with this ghostly particle called the neutrino. And there are several reactions that take you from protons all the way to helium-4. And they predicted the flux of neutrinos. And that's what Mccall and Davis were trying to measure. The origin of neutrinos in terms of science is a long and interesting history. It was postulated by a theorist, Wolfgang Pauli, who is shown here, more than 90 years ago. And he invoked it as a desperate remedy to save the law of conservation of energy. And then the idea was followed up by Enrico Fermi, an Italian physicist. And since he was Italian, he called it a small neutron, or neutrino, hence the name. And he created the first theory of weak interactions. And then the number of people tried that we should try to detect it, but this was considered for a while impossible. So Hans Bethe, who was the guy that I mentioned earlier, who created one of the models of stellar energy generation, in the 30s firmly believed that it would be impossible to ever detect the neutrino. And yet in 1957, a group led by a couple of Los Alamos scientists actually managed to do so. And they placed, by placing a large detector next to a nuclear reactor. Their first idea was to place the detector next to a nuclear explosion test. they were dissuaded by their colleagues, saying it would be difficult to collect the data from this. So the reactor was the next best option. So in the Nobel Prize lecture, Frederick Reines has this quote, "Why did we want to detect the free neutrino?" Because everybody said you couldn't do it. So sometimes this is a good motivation for scientists. So this is the tour into the origin of the neutrinos. Now, again, we go back to 1987. In the home-stake experiment, we detected neutrinos from the core of the sun. So this was this solar neutrino detector that I was talking about. Was 8 light minutes away, so that's relatively close by astronomical standards. But the neutrinos in 1987 arrived from another galaxy, which is much, much farther away. So the source of this burst had to be absolutely mind-boggling. So you can make this estimate. There's an explosion. Neutrinos are emitted in all directions. You put the distance to the Earth, and you compute the flux of these neutrinos on Earth, and you say, I detected 24 neutrinos, knowing the size of the detectors, how many neutrinos were emitted. And neutrinos are tough because they are extremely weakly interacting. So a typical neutrino in this energy range can travel through a light year of water without scattering. So that's why these detectors are big, and you detect only very few. So you can work backwards, and you say, I detected 24 neutrino events. I know the size of my detector. I know their probability to interact from theory and the distance to the explosion. And then I can infer the total energy emitted on neutrinos. And then if you do that, it turns out that the energy of the neutrino burst is actually 100 times more than the visible explosion, which is already amazingly bright. So you could see supernova 1987A with a naked eye, even though it's in a different galaxy. For a few months, you could see it with a naked eye. And so where does so much energy come from? So the energy comes from the collapse of this core. And again, you can do an estimate by saying that I have this core. It collapses to nuclear densities, so I know this radius. And using E equals mc squared, we can estimate that this gravitational energy is about 10% or so of the rest mass of this core. So that's amazing. So there's no other known way in our universe to convert rest mass to energy with such efficiency. So nuclear reactions take maybe a percent or so of, or less of the energy of the mass and convert that into energy. And gravity in these extreme objects can take as much as 10%. Now, these numbers are interesting because they tell you that the classical physics is at the edge of its usability. I mean, I'm using here classical gravitational estimates, but what this tells an expert is when energy of gravitation becomes comparable to the rest mass, then you should use general relativity more properly than classical physics. Nonetheless, you can get at least useful order of magnitude estimates from classical physics. So the core of the sun collapses to an object like this. So this is a neutron star that's finally formed out of this collapse. I put it on the map of the Bay Area. So you can drive from one side to another in about 15 minutes. Goes from about Foster City to Cupertino. So the Apple campus is here. So it's not, it becomes a very small object, and there's a lot of mass. So there's a lot of energy that is released when it gets compressed to such high densities. And this energy is carried out of this core by the particles that have the easiest time to escape, and that's where the neutrinos come from. So photons, particles of light, would take a long time to diffuse because the cross sections are relatively large. And even neutrinos don't stream freely. This object is so dense that even neutrinos get trapped and they bounce around. But they escape, and they escape in about 10 seconds, and that's the explanation for the duration of the neutrino burst. So from the point of view of energetics, you have this core, it collapses, 10% of its rest mass is released on neutrinos, and a tiny fraction is diverted into a visible explosion. Of course, the visible explosion is very important, not just because we see it, but because it makes and spreads out heavy elements, including oxygen you're breathing now. It was once made in one such explosion and expelled and thrown in the interstellar medium, which then collected into the solar system, and here it is. So it's very good. Now then, also this process is known to see the formation from subsequent stars. So thanks to neutrinos, we have been able to look inside of the sun and confirm that indeed there is a thermonuclear reactor happening there, and in the supernova 1987, and confirm that there is this core collapse that happens, which powers a tremendous burst of neutrinos and the visible explosion. So in 2002, these two gentlemen got the Nobel Prize in Physics for these amazing discoveries. What can we do? Can we do more than peaking in this with a few events? The answer is yes, and that is a very exciting possibility for the next several decades. So in our galaxy, supernovae are thought to occur once every 30 to 50 years. So I explain this to my students as like about the same frequency as major earthquakes in the Bay Area. So in both cases, it pays to be prepared. And so in the case of supernovae, it means that we have large detectors, and we have to make sure that when the next burst comes in, that we can get the optimal information from them. So there is a new generation of experiments that is operating now, and there are even more impressive ones being built. So there is something called the Super Kamiokande experiment in Japan, and this is going to be superseded by an even larger Hyper Kamiokande detector. So these are descendants of the original Kamiokande detector that I told you about. In the US, there is an experiment called DUNE, Deep Underground Neutrino Experiment, which is being developed, and it is thought to have 40,000 tons of pure liquid argon with advanced electronics, and it's international collaboration, and the cost is over $1 billion. And you say, now, why? What happened? Why are they using my taxpayer money for this? Remember the story of missing solar neutrinos? I didn't tell you how it ended, but the ending is also very interesting. It was not an experimental failure that there was a discrepancy. And theoretical predictions for the solar neutrino rates were exactly correct. And since we learned that neutrinos were produced at the right amount, but some of them were transforming into another type of neutrino, or as we call flavor. This is one of the biggest discoveries in particle physics in the last 3-4 decades. So the bottom line here is that neutrinos come in 3 types, at least 3 types, where each of the type has a corresponding partner, a charged particle. There is something called the electron neutrino, which comes with electrons. When you have weak interactions that create positrons that you saw them, you create electron neutrinos, but it turns out that the electron has 2 heavy partners, a muon and the tau lepton. The tau was discovered here in California. The Nobel Prize was given for it in 1995. It was discovered in the late 70s. So each of them have, so each of these charged leptons, as we call them, has a corresponding neutrino type. And thanks to quantum mechanics, solar neutrinos, which are initially created in this state, get partially converted into the other 2 types. So this is a very important development in particle physics that took place in the last 2 decades. So the decisive measurement came from the SNO experiment, Sudbury neutrino experiment. It came online in the year 2000. It measured neutrinos from the sun, but in 2 different ways. One method was sensitive only to electron neutrinos, and another one to all three flavors that I described. The total flux in all flavors came out as predicted, and the electron neutrino flux was measured to be 1/3. And so we discovered that neutrinos are massive, and they what's called oscillate. They change their flavor on the way from the sun. We have also seen that this phenomenon happens with neutrinos that are created in the Earth's atmosphere. And so there are follow-up detectors. So the follow-up detector to Kamiokande is a super Kamiokande, this gigantic volume instrumented with photomultiplier tubes. This is a boat of people who are working on it as it's being filled. And so they measured the atmospheric neutrinos produced in the atmosphere. They found that neutrinos that come from down, muon neutrinos, are depleted compared to the ones that are coming up. So there is a distance-dependent disappearance. And that was another confirmation for neutrino flavor oscillations. So there's a flavor, there was a Nobel Prize given in 2015 for this discovery. And so this brings us to today. So now that we know neutrinos are oscillate, the field is turning to precisely measuring these oscillations. These precise measurements can reveal some physics that violates some or violates some naive basic symmetries of nature. And without going too technical, that's the reason why the Dune experiment is being constructed. There is a beam of neutrinos created at Fermilab in Illinois. It's shot on the ground to a detector in South Dakota. And this detector, in addition to measuring these oscillations, can also wait for the next supernova. So in this case, many thousands of supernova neutrinos are expected to be seen. And then the question is, what do we learn? The hope is that we will learn in details how this explosion develops inside second by second, because we're getting neutrinos directly from the collapsing core, whereas the visible light only comes when the shock wave disrupts the outer layers. So neutrinos are expected to be very important in our next supernova observations. We will learn many things, including how matter behaves when compressed to nuclear densities that you cannot achieve ever in a laboratory, and how neutrinos change flavor in this condition, and whether there is new physics. So I want to end here because I think this right now is a very interesting story, and we are waiting for the next galactic supernova. Sometime in the next several decades, for 10 seconds, there will be an enormous burst of neutrinos from a collapsing core of a massive star somewhere in our galaxy. And we're trying to figure out how to build detectors accordingly to be ready. So it'll be a talk here by Ines Gilbotea, who will tell you about detection, which is a very interesting story. And I will pass the baton to her in this way. One thing I want to say is that this is a teachers' conference, right? So it's very important. We all remember teachers in our life who made a difference. So for scientists, it means teachers from elementary school all the way to your postdoc advisors. So I wanted to mention John Mccall, who was a great mentor and a teacher to many of us. Here's a younger version of me, much younger. Anyways, so thank you, teachers. How am I doing with time? Am I over? Am I okay?
No, you're excellent with time.
Okay.
Thank you, Alex, for this inspiring talk.
So what do we do? Do we do questions and answers?
Yes, there are questions.
So you mentioned so many different detectors that are getting ready. Are they ready now?
So Super Kamiokande is ready now. And in fact, they have been very concerned to minimize any downtime for the last 20 years because they don't want to miss this opportunity. What if they have maintenance for a couple of days? The supernova happens, and then you have to wait another 40 years. So there are some detectors ready, and there will be this next generation of detectors for something called these lone baseline experiments, where you create neutrinos in one state and you shoot them on the ground and you measure them in the other state. So they are being developed and constructed. So they will be even more impressive than the detectors that we have now. So if the supernova were to happen tomorrow, we would already get a great deal of information. But if the supernova was kind enough to wait another 10 years, then we'll be in even better shape because we will have these next generation detectors. And I mean, I can explain why it would be great to have both Hyperkamiokande in Japan and this Dune detector. It turns out that they're sensitive again to different types of neutrinos, and you want complementarity of that information.
Hi, thank you for your talk. So you mentioned that neutrinos are super hard to detect because they can travel great distances and only interact very weakly. What are those weak interactions that you look for in detecting them? Right. So the neutrino is very particular compared to other particles because other particles like electrons also possess these weak interactions. Weak is not just a statement of weakness. It's not just an adjective. It's a technical term. There are interactions which are called weak, right? Where you have a neutrino, it interacts with the target and it turns into an electron. So it gets close to a nucleus. It exchanges something called the W boson, which is a heavy virtual particle that we now know exists, and it turns into an electron. If it's an electron neutrino, or if it's a muon neutrino, it turns into a muon, and it looks very different in the detector. So weak interactions are interactions that are responsible for radioactive decays. They're very important for understanding all the elements in our world, but they're difficult to see. So this whole history of studying radioactivity, Marie Curie, nuclear bombs, all of that, requires precision observations. But things that are responsible for beta decays are also the same things qualitatively that are responsible for thermonuclear energy of the sun. You take protons, you assemble them, and in the process, some of them turn into neutrons. So this process of turning a proton into a neutron while emitting a positron and a neutrino is a weak interaction process. It's different from electromagnetic, where you just have charges and you exchange things, but the particles do not change their type. It's different from strong interactions, where you exchange something called gluons, and it binds quarks together and makes protons and neutrons. But yeah, so weak interaction is a technical term for a certain type of process that's rare in everyday life, but it's absolutely essential for understanding the world around us.
This is a follow-up to the first question. Thinking about the NOVA detector in northern Minnesota, which is
right
off axis for a beam of neutrinos coming from the Fermilab, would that still be useful in the event of a supernova?
It would be useful. I mean, there is an estimate for NOVA as to what they can see in terms of a supernova signal. It's on the surface, so there are some backgrounds to contend with, but there's still some estimates. It's a fast detector in a technical term. It reacts very quickly, so it would be useful. I mean, there are estimates, there are papers, information that you can extract from that. Not as useful as this generation of detectors that I'm talking about. But, yeah.
Thank you.
We have a couple of questions from the online audience. So Jim in Kansas says, or asks, are we able to determine direction of a supernova with the current detectors? Can it tell the optical astronomers where to look?
Yeah, that's an excellent point. So the pointing capability is one of the
topics of research, basically how well you can point. So neutrinos, when they come from a supernova, they interact in different ways. And these different ways depending on which detector you have. So most of the interactions happen on nuclei. The probability of a neutrino to interact with a nucleus is higher, but the distribution of the final product is more isotropic. There is also a possibility, it's a smaller, but still important, that a neutrino will interact with an electron in the target. The thing about an electron, it's light, so you kick it in the same direction, so then the created final state particle points in the direction of the neutrino with some opening angle, but that's not a large opening angle. So for hyperchemical and also for Dune, there are studies of pointing capability, and there are ideas that within some opening cone of perhaps a few degrees, we will be able to tell astronomers where they should look. From this subset of events, which is rare. So basically you look at your distribution and you see most of your events are kind of isotropic, but there is a subset which all point in the same direction. And you have to be able to tell astronomers, go look there.
All right, and then Andrew in New Jersey has two questions. One was, you mentioned that the Kamakande detector had retrofitted their director, which lowered their threshold. And he wants to know, do these new detectors have an even lower energy threshold?
They certainly have low enough energy threshold to detect the bulk of the neutrino flux. There are two reasons why at the very low end we still have problems. One is that it takes energy to excite an argon nucleus. It's called something called the Q value, technically speaking. So at the very low end of the neutrino spectrum, you will not be able to see those neutrinos because of that. And second is the cross-section, the interaction cross-section of the neutrino grows with energy. So there will be more neutrinos in the 20, 30, 40 MeV than there will be in, let's say, 10 MeV interacting. But yes, so there is obviously a concern to keep the threshold low. And most of the neutrinos will be detected, but not the entire spectrum still.
Okay, thanks. So his other question was, do different flavors of neutrinos have different energies?
When you, so this question might take some time to unpack. When you create a neutrino in the sun and it flies to you and it changes flavor, then as it changes flavor, it keeps the same energy up to quantum mechanical uncertainty principle, which is actually what makes the flavor transformations possible. Flavor transformations as a quantum mechanical process is based on the uncertainty principle. But yeah, from the point of view of experiment, that neutrino, which is created in the sun, which travels to our detector, has basically the same energy as it converts flavor. So that's a statement on neutrino oscillations. In the case of supernova neutrinos, there are initial neutrinos that are emitted not only in electron flavor, but also in the mu and tau flavors. And the oscillation phenomena swap them. So what you see as an electron neutrino has not only the signal of the initial emitted electron neutrino flux, but the impact of oscillations. And these oscillations can mix up the spectra of the initial neutrinos, which are different. That maybe is a bit too long, but there is an interesting possibility there to learn about physics by studying the details of these oscillations.
So maybe this is a naive question, but following up on the weak interactions, is there some threshold, some way of identifying which one of the neutrinos are going to actually interact? Like, is it something about its exact path toward another nucleus, or like, how does that work?
So when we make a neutrino in the lab, a given neutrino is likely to never be seen again with an overwhelming probability. So this is different from electrons. You make an electron, then you can follow it around and so forth. And you make a bunch of neutrinos at Fermilab. You know, they're talking about numbers like 10 to the 20 or so of neutrinos that they might create. And most of them will never be seen again. So it's a law of large numbers. You need to create so many of them that in the detector far away, you have sufficient numbers of interactions that you are still able to measure the physics that you want. So, you know, it's a different strategy between normal particles and neutrinos that we have. I mean, these are fish that creates thousands and thousands of little fish babies, and most of them get eaten, but the few that make it there are important.
Okay, I have two detector questions. You mentioned IMB. So what type of detector is that and what happened to it? And then IceCube, how does IceCube fit into this?
Oh yeah, so IMB was the same type of detector and as Kamiokande was a volume of water surrounded by photomultiplier tubes. These are technically called the water Cherenkov detector. Cherenkov is the process that particles use to emit light, which is then registered. It's called the Cherenkov radiation. And so IMB was the same concept as Kamiokande, which is the same concept as a super Kamiokande, which then confirmed oscillations, and which is the same concept as the hyper Kamiokande. You go one order of magnitude in size, thinking every time you do that, it will give you another Nobel Prize. It worked 2 times already, so people are hopeful for the 3rd time. The IceCube detector is a different game. It uses strings which are drilled in ice, and they're further apart, so you're not able to recreate cones of Cherenkov light the same way that you are able to do in Kamiokande, but you instrument a huge volume. So what you will have is a very large number of hits, a single detector hits. So you simply look at your noise level, and it turns out that your noise level when the supernova comes just shoots up, because that's not noise, that's supernova neutrinos interacting within the vicinity of each of these detectors. And there is also, you know, there are studies of how you process that signal and what you can extract. You don't measure the spectrum, but you measure the flux of neutrinos with very high statistics, because you just have so many of these interactions, because it covers such a huge volume of ice. So yeah, IceCube has as a day job, it looks for neutrinos from distant sources and or atmospheric neutrinos, but it also moonlights as a supernova detector.
Do we have one detector that can detect all 3 flavors, or what is the modifications needed to detect different flavors of neutrinos?
Right. So in the case of the snow experiment is remarkable because that detector was specifically designed to detect all 3 flavors. It's not easy. You need to design your detector to be sensitive to a different process. So normally, as I say, the process is you create an interaction, a neutrino turns into an electron, and then you know that this was a neutrino of the electron flavor, but it's only sensitive to the electron neutrino part of the flux. And snow could do that, but it could also detect what are called neutral current weak interactions, which are interactions where the Z boson is exchanged. The neutrino remains a neutrino, it exits the detector, but what happens is that the deuteron, so the snow detector was made of heavy water, which are made of deuterons. The deuteron is dissociated, a neutron is kicked out, and then they designed their detector very carefully to count those neutrons. And by counting those neutrons, they were able to measure the rate of all interactions. So that's why the Nobel Prize is richly deserved. But not every detector has that capability. And we're trying to understand in the case of each of the detectors what capabilities they have and how to optimally use it.
We have a talk by an experimentalist right
Yeah,
after lunch,
right.
so hold all your detectors questions
Yes, very good.
for her.
Very good. Ines will tell you a lot more in a lot more lucid details than I can.
Thank you. Just wanted to know what might be the basis for us to expect an explosion, supernova explosion every 30 years?
Right. So, well, that's a very good question. So we know the rate of stellar formation in our galaxy. We know the rate with which new stars are formed by observing the galaxy. And a certain fraction of them will be above this mass. And so we can estimate how many of massive stars are formed at the current star formation rate. The estimates vary. If you look at our local neighborhood, so you can say, well, they're visible explosions, they're only seen once every several hundred years. That turns out to be because most of the explosions in the disk of the galaxy are expected to be obscured by the dust. So if you take the nearby rate and you extrapolate this to the rest of the galaxy, you get something like 5 per century. We think it's an overcount because we're in the spiral arm where there is an active star formation process. But people come up with numbers like 1, 2, 3 per century, which look plausible. We can also observe galaxies like our own and observe that rate. And there are several galaxies where people observe several supernovae since observations began. But basically, that's the argument that, first of all, galaxies like our own have a similar rate to 1 to 3 per century. And second, the theoretical estimates predict that.
Is it that the explosion lasts only for 10 seconds? And did the neutrinos exist before the 10 seconds, or are they a product of the explosion?
They're a product of the explosion, yes. So the neutrino burst exists for 10 seconds. The actual supernova becomes visible for many months. So there is this collapse which releases a lot of energy that got liberated by compressing things gravitationally. And then that energy has to be lost. So the plasma is so hot that there are electrons and positrons created, and by weak interactions, they make neutrinos. And electrons and positrons and photons themselves are stuck because it's so dense. Neutrinos diffuse out the easiest, but they are created inside. They're not like there was some set of neutrinos. In fact, there are about 10 to the 58 neutrinos that are emitted. There are about 10 to the 57 nucleons in this collapsed core. So there are about 10 or so neutrinos per each nucleon in this collapsed core.
Do any gravitational wave events produce neutrinos that you can detect?
Well, cataclysmic events in the universe can produce neutrinos, but also gravitational waves. So waves themselves don't produce neutrinos, but the events that create them could produce gravitational waves. Gravitational waves are sensitive to the dynamics of how things orbit. So it's the sloshing of the matter that produces a gravitational wave signal, whereas neutrinos tell you about the total energetics of the explosion. So in the next galactic supernova, you can get both gravitational waves, which will tell you about how things were sloshing, and neutrinos, which were telling you the energetics and many other things about the explosion. So an ideal situation is we're going to get both, and there will be thousands of papers written putting these signals together.
And one other question, would gravitational lensing produce maybe a beam of neutrinos if you wanted?
Yeah, well, gravitational lensing deflects light, and it would also deflect neutrinos a little bit. But in practical terms, the amount of deflection is not enough to, for example, make an explosion that's otherwise invisible to be visible. It's unfortunately not powerful enough to zoom in onto some distant explosion. But neutrinos would follow the gravitational lensing.
I got it right there.
In 1987, there were 4 detectors online. Wasn't Mount Blanc also online? And didn't they see neutrinos like several hours before for the supernova burst? Has there ever been an explanation to the Mount Blanc data?
There's a controversial measurement, what, if anything, they saw. And I recuse myself on this one.
Very good.
I only tell you the ones that fall into a coherent picture. There is no scientific agreement about this other one, what to make out of it.
See, and I'll take director's prerogative as well to say the time it takes between the neutrino collapse and the first light is the shock wave traversing the star. And in this case, it was a few hours. Most of the supernovae are seen, it's about a day. So there's uncertainty as well in that time, but whether it's going to be short. This is a blue supergiant, but red supergiants, it takes about a day for the shock wave to get to the surface. So that's also going to be very exciting.
Yeah,
astronomical.
We'll tell you how fat your hydrogen envelope is, which would be very cool.
Yeah. One more. It totally is a function of the size of the star. That's right. Yep. Yep. Okay.